Alright everybody, welcome to our next video here. In this video we're going to talk about pointers, and hopefully at this point in time you've seen and realized the importance of a pointer and being able to understand, recognizing and understanding the use in our programs, especially when we're trying to disassemble something or trying to reverse it. So all variables are pointers. Right? Everything has an address. It has a location somewhere in which we can store that data in memory. When are pointers not a pointer? Well, that might be when they're registers, and so sometimes you'll see, depending on, that data might be moved directly into a register in which we're referencing that data in that register directly, right? We also, and oftentimes, will move addresses into those registers, in which case then if we want to access the data that they're referring to, we have to dereference those. In non-optimized code, and we haven't talked a lot about this so far in the course, but what compilers will often do is they will oftentimes try to optimize your code. They'll optimize it for size, they'll optimize it for performance and speed. And so you can, and if you look at your compilers, you can look at Visual Studio, you can see that there are a variety of options that you have in order to tell the compiler if it should optimize your code, maybe it shouldn't, maybe you don't want it to, and then if it does, the kind of optimizations that you prefer. And non-optimized code, and that's by and large what we're kind of looking at, although you'll start to see a blend of it here as we get further along in the course. Variables are stored on the stack, as well as addresses also being stored on the stack. And optimized code, and this will become even more relevant when we start talking about calling conventions, is that sometimes the compiler will find a way in which to use a register instead of using an address, instead of using the stack or using memory to save or to pass values. For example, let's say that you have a function call. Normally we've talked about functions, and we've seen in a lot of our examples and exercises, we've seen arguments being pushed onto the stack for that function. Well, a compiler might see that your function only has one argument, and so maybe it'll optimize that to use a register to pass that argument instead of using the stack. Using that register would be more efficient, it would be quicker. So you can see those kind of changes in the code, and you will see some of those in some upcoming labs. So let's take a look at just how we can look at pointers and see their use inside some sample programs. Here you can see a relatively straightforward program, and this is essentially all this program is doing is it's iterating through all of the command line arguments provided to the program and printing them off. And so you can see you have argc, argv, and environment p. You'll probably have noticed over the years, as your experience with programming in C and C++, that how someone defines main can be varied. You can see just void in there, you can see I think nothing at all, you can see argc, argv, you can see argv being an array of pointers. Right? There's a lot of different ways in which you'll see this defined. What these are being used for, argc is telling us the number of command line arguments, and argv is a pointer to those command line arguments. And so if you run any program from the terminal, and let's say that I want to run the file program. I gotta see what files I have here. I'll do this thing here, right? File is the name of the program, and this was one of the arguments. And so when we look at that, what that is telling us, argc would be 2, because we'd have the name of the program itself as well as one argument. Right? So the number of command line parameters, and argv would be a pointer to this, the name of the program, and to this, the value of the argument. Right? And so that's what those two are allowing us to do. They're allowing us to reference that is passed into the program from the command line when it's executed. So what this is doing, you can see that there's a loop, I is less than argc, and what we're doing is we're simply looping over the number of command line arguments and then dereferencing argv and printing it off. Right? --%s, new line, argv, so we're printing it off. Argv, it's a char pointer, and so what this is this is an array of pointers to strings. It's an array of pointers to string values, and so in order to dereference, we have to dereference one of those and print it off. And so what you can see in this loop is it's going to go through each one of those and print it off. If we look at the disassembly then, you can see that this is what the disassembly gives us. Okay, we can identify some of those control structures because we can see that there's a loop right here. The arrows provide that information for us. What we're interested in and what I want to kind of focus on is really this dereferencing of argv. Okay, so if we look at where in the code we're doing that, we can see that in order to dereference argv, it's going to be right before a printf call. After that, and I'm also interested in how we're incrementing argv, we can see that pointer increment right there. So we look at this, we can see that we push EAX and then we push the offset. So EAX is going to be the value that we print. We can see here we move into EAX, EDX, right? But we also are dereferencing. What is EDX? Well, if we trace that up, we can see that right before that we move into EDX, argv. And so what IDA has done is it has determined that this is our main method right here. Okay, there's argc, there's argv, and then there's environment p, which we're not talking about. There they are. And so what it did was we moved argv into EDX right here, and then EDX was dereferenced. Remember that those brackets around that register mean to dereference it. This is a pointer to an array of pointers. So we have to dereference in order to get that element, that address out of that element. So argv is moved into EDX, EDX is dereferenced, moved into EAX, EAX is now pushed in preparation of this call to printf, right? And so we're printing the string value, not the address. Okay, call is done, we have stack cleanup, and now we move on. So the next instruction, or series of instructions that we're interested in, is how do we iterate over those? Right? In this example, we're not accessing each element. Right? Normally, you would see when we access an element of an array, you might see argv bracket, and then we use I. We use I to access each element of the array. Well, we are using I for the counter, for the loop, but what we're doing here is we're just incrementing the pointer using this plus. And what you're looking at here, what this is doing is it's actually changing what argv is pointing to, right? If it's an array of pointers, well, we're incrementing where that pointer is. So we're changing it. So instead of it pointing to, index 0, index 1, index 2, and argv pointing to the base of that always, and us referencing those elements by using this type of syntax, we're changing where argv is actually pointing to. So after we increment the pointer, instead of pointing at index 0 or element 1, it's now going to point right here. So how do we do that, or how does that look when we disassemble that? Well, you can see here are those instructions. Okay, so this little group right here. Okay, argv is moved into ECX. We add 4 to ECX. ECX is moved back into argv. Okay, 4. We didn't do plus, we didn't add 1. When we do pointer arithmetic, which is what's happening right here, then what happens is the size of that pointer is added. Right? Pointers are 4 bytes, and that's why we saw in this disassembly, we saw add to ECX4 instead of add to ECX1. Okay, so that's what's happening here. So make sure that you understand what's going on. This is pretty much in this block right here, right? Because we did a couple of things. We dereferenced argv to print, and then we also incremented that pointer. Okay, the next one, a little bit more straightforward, and this is, I guess, more of a review really than anything for arrays, is that you can see that inside of here we have x being incremented. While x is greater than 0, x plus plus. Okay, so what you have here, and I just realized there's a mistake in this program, but it doesn't really matter because this isn't all that big of a deal to focus on because we're not going to run it. The condition will never be false. So I said, well, x is greater than 0, x plus plus, x starts at 12. So this condition will never be false. So this loop will never break. So don't run this program. What you'll see here, though, is that we're incrementing the value of x. So we're going to have x as a local variable. So it's going to be declared on the stack. And I just want you to see that how that is being incremented and how that differs maybe from the dereferencing of the pointers to print argv in that previous example. The other thing you'll see here is x is multiplied by itself, and then it's stored in array x. So you'll just see how that calculation is done, storing it there. Okay, this is a little bit harder to see, so I'm going to zoom in a little bit. Here you'll see the first loop identified right here with this loop. You can see that var4 So var4, if we go back, we have our counter, essentially what becomes our counter variable x right there. And so var4 in this case is x. So here x is initialized, so we can make that x for var4. Okay, this is our loop, so there's our comparison and our conditional jump. So var4 is moved into EAX. We add 1 to EAX. EAX is moved back into var4. Right? What this is doing is this is moving into EAX the value at EBP plus var4. Right? It's not moving an address. It's moving that value. So EAX has in it, after this first instruction, whatever value is EBP plus var4 points to, which is location on the stack. If we wanted an address, or for some reason we needed an address, we have an instruction that we'd have to use. And that instruction is LEA, load effective address. Okay? LEA, instead of move, would load an address into EAX. This moves the data. Okay, we want to increment that. So we move the value at EBP plus var4 into EAX, add 1 to it, move EAX back into var4. This is an increment with a normal integer variable, not a pointer. So when we do x plus plus here, we do in fact just add 1 to EAX. In the previous example, we did the increment operator on a pointer, and so you saw add to EAX 4 because the size of that pointer was 4. It was incrementing the pointer based off of the size of the elements to the next element. Okay? Here, we're just incrementing an integer value. Once that loop's done, we'll move on. We'll execute the second loop, which you can see is this right here. So that's a for loop. This handles right here our for loop incrementing our counter variable, because with the for loop we specifically define that counter variable, and then this is the inside of our loop, right? And so var4 is the counter, moves into EDX. We multiply by var4 by EDX, so this is x equals, well, that's x times x. We move var4 into EAX, and then we move dx into this. And so these instructions right here handle the assignment. Okay, so dx, we're dealing with an array of shorts. Shorts are 2 bytes, not 4 bytes. So what you can see in those instructions then is that dx, 2 bytes of a 4-byte register, gets moved into this location. And then var58, this is being used to calculate the appropriate offset for the array. EAX times 2, you know the array is 2 elements. We can assume it's a short. And then that's how that's being moved into there. So I won't go spend too much time on that just because we had a video dedicated to looking at arrays and how they're used. Okay, and then once that's done, we will jump to the end of our program right here. You can see the cookie check and then the return. Okay, last thing we'll talk about here in this video is malloc. And malloc is a little bit different in where the memory is actually allocated when a malloc is called. It's not allocated on the stack. It's allocated in an area, in a section between the code and the stack, the text and the stack. So here's our stack. Our stack grows down, which you can see here. Here's our text section, which is where all our instructions are for our program. And then the heap, and the heap grows up. And this works out pretty nicely because this allows both the stack and the heap to dynamically grow and adjust with the remaining space in the address space for that program. They can potentially collide if your program used enough of them, but generally we don't worry about that. Right, so they're both going to grow towards each other. When it comes to using the heap, we have different ways in which we allocate memory, and malloc is the primary way in which we do that. So here's an example where I have an int, a char, and a short, and I malloc memory for each one of those. Now I assume that you've used malloc before. So malloc takes one argument, and that is the number of bytes that you want to allocate. So we could have malloc 10 times the size of int. So we can have a pointer that then can essentially operate using malloc as an array. This can be an array of ints. This can be an array of chars. This can be an array of shorts. Right? So we can allocate enough memory for a single instance, 4 bytes for an int, or an entire array if we want to. So we'll malloc that memory. We'll have pointers, right? The asterisk here defines that as a pointer. So S is a pointer to data that is short. Y is a pointer to a char, and in this case it's going to have 107 bytes. In this case it's going to have 40 bytes. In this case it's going to have 4 bytes, right? So it's going to point to that much data for however much we allocated using malloc. Okay, once we've allocated that memory, then we'll dereference those pointers in order to store data in those locations. If we didn't dereference, then what we would be doing is, if we didn't dereference, what we'd be doing is we'd be accessing the address itself, right? Because a pointer, the value of a pointer is an address. We dereference that address in order to store data. Okay, so we'll dereference that. Okay, here's that program. Okay, generally, when we're looking for calls to malloc, IDA does a pretty good job for the most part of identifying that, a call to malloc. So we see a call to malloc with the size of the data, which you can see right here. Okay, so you see a push and then a call. What is returned? What is returned from malloc? A pointer, right? And we can see that. So after that call to malloc, our stack is adjusted right here, and then we return the value in EAX into var8. Okay, so there's a malloc var8, there's a malloc to var4, and then here's a malloc varc. So var8, var4, and varc are all of our pointers for that memory that we just malloc, that we dynamically allocated in this program. We can figure out which one's which, either contextually or just through the size if we wanted to. It's really not all that important at this point in time. When it comes to using those then, okay, so this is really right here. This separates the last assignment. Okay, here's our move EAX into varc. Now we want to actually use those locations. And so if we look at that first example, we dereference X and we move 125 into it. So let's see here. I should have just opened this up in IDA, but I didn't. All right, 7D in hex is 125. Okay, and that I would assume would be the first instruction, but I just wanted to make absolutely sure. Okay, so that's 125. Okay, so varc, var8. So this var8 right here, var8 right here. That's our int pointer. And what did we call that? I think we called that X. Yes, we did. Okay, so that's our int pointer for X. Alright, so var8 gets moved into EAX. You can see we now dereference EAX right here and move 125 into that location. You'll also notice in front of it there's this D word pointer. And what this is saying that we're going to dereference this location in EAX, right? Right before that, EAX has an address moved into it. So we're going to dereference that, and it needs to know the size. So we're saying that this represents a D word worth of data, 4 bytes of data. That way, because when memory is allocated, it's all going to be contiguous. That way we don't have to worry about if we try to move more data than 4 bytes worth into this location, we can see that there'd be a size mismatch. And so we only have 4 bytes available at this location, right? Because we're just referencing one element of that array. So that makes sure that's what you see. That's what this D word pointer is saying. It's saying we're going to dereference this location and we can move at most 4 bytes or a D word into that location. Okay, and then for the last one, 22 hex. We're dealing with our, let me zoom out here, dealing with our short, right? So what we're doing here is 22 hex is our value. We move that into EDX. We now move varc, which is our pointer, into EAX. DX, because we're dealing with a short, we don't have the cast. We have DX being moved into dereferenced EAX. So again, we can see a slight difference there. And so it's important to be able to identify when something's being dereferenced, when a pointer is being dereferenced, and how data is being moved into and out of that. Okay, the last few instructions here are just our epilogue. So XORing EAX for the return, and then epilogue right here. Okay, so we don't have to worry about the rest of those because we've talked about those already. All right, so that's all I have for this. Just hopefully a slight refresher, as well as just looking at how pointers are used in IDA a little bit more detailed. That's all I have for this video. So again, let me know if you have any questions. Otherwise, I will talk to you guys in the next one. Thanks.